Hey friends, I am Abhishek Parab and welcome to the tutorial series on basic electronics titled as Monostable and Astable Multivibrator. In this tutorial, I will be explaining you about internal circuitry of IC555 and also we will see its working as Astable Multivibrator and Monostable Multivibrator. IC555 is a well-known component in electronic circuits, but what is not known to most of the people is its internal circuitry and function of various pins present there. So to start with, why 555? Why it not called 1, 2, 3 or 5, 6, 7? Because it has three 5 kilo ohm resistors in series inside it. So let's move on to the internal circuit. Yeah. As shown in the diagram, the IC555 consists of two op-amps, IC1 and IC2, used as comparator, along with RS flip-flop as a bistable element. In addition to that, an inverting buffer, IC4, is incorporated at output stage. For simplification, I have separated this diagram in 5 sections, namely A, B, C, D and E. In section A, it consists of 3 resistors R1, R2 and R3 connected in series. Here R1, R2 and R3 are of equal resistance, that is, we have seen before 5 kilo ohm. Hence, supply voltage gets divided equally across 3 resistors. That means at junction J1 and J2, voltage will be 2/3 and 1/3 of VCC respectively. In section B, op-amps used are in comparator mode. These are used to compare voltages at threshold and trigger inputs, with the voltage fixed by potential divider due to R1, R2 and R3. Section C comprises of RS bistable stage flip-flop. It can be either set or reset based on output from section B. In addition to that, external reset input is provided to reset that flip-flop. In section D, an open collector transistor switch TR1 is used. This transistor is used to rapidly discharge an external timing capacitor. When base becomes positive, transistor conducts and shorts external capacitor to the ground. And then comes final stage. Stage E. In this stage consists of an inverting power amplifier. It is capable of sourcing or sinking required current to drive a small relay or resistive load connected to output pin. Now, as we have seen that the 3 resistors R1, R2 and R3 divide the voltage in 3 levels, that is VCC, 2/3 of VCC and 1/3 of VCC. So at IC1, that is lower comparator, the positive non-inverting potential is at 1/3 of VCC. So when the voltage at negative inverting pin of the IC1, that is trigger input, goes above 1/3 VCC, the output of the IC1 comparator becomes high, and that sets the RS flip-flop, and in turn it sets the output of the IC555. So when it sets, the inverting output, that is Q bar, becomes low, and which in turns off the transistor. So when we turn on the power supply, external capacitor starts charging. We can see that at IC2, that is upper comparator, non-inverting voltage is at 2/3 of VCC. That means that the output of that comparator will become high only when the non-inverting terminal of the IC2 becomes above 2/3 VCC. So when that capacitor voltage increases beyond 2/3 of VCC, output of the op-amp becomes high, and that resets the flip-flop. So when that resets, the Q bar becomes high, and that turns on the transistor. So when transistor turns on, since the external capacitor is also connected to the discharge pin 7, that shorts the capacitor to the ground, since emitter of the transistor is connected to the ground, and when that voltage becomes capacitor voltage increases above 2/3 VCC, it starts discharging through this transistor. So that's all about the internal structure. IC 555 has various applications in various fields, but mainly these are used in various working modes like astable, monostable, or bistable multivibrators. For time being, we will be only seeing its working as astable and monostable multivibrator. Astable multivibrator. So this is the circuit diagram for astable multivibrator. Here you can see that pin number 2 and 6 are shorted to the capacitor, and there are two resistors R1 R2. Their values R1 is 150 ohm and R2 is 1 mega ohm, and C1 is 1 microfarad. When power is turned on, trigger pin voltage is below VCC by 3. That makes lower comparator output high and sets the flip-flop, and hence output of 555 IC is high. This makes transistor off. As it is off, capacitor C1 starts charging, and when its voltage exceeds VCC by 3, lower comparator output becomes low. But since output of upper comparator is still low, flip-flop output experiences no change. But when capacitor is charged to voltage above 2/3 of VCC, upper comparator output becomes high, which in turn resets the flip-flop, and output of 555 IC becomes low. As soon as output becomes low, Q bar becomes high and transistor is switched on. So capacitor C1 starts discharging through R2 and discharge pin 7. So as capacitor voltage gets down below the 2/3 VCC, upper comparator output becomes low, but flip-flop remains in its previous state as both comparator outputs are low. While discharging, when capacitor voltage gets down below VCC by 3, it makes lower comparator output high and sets the flip-flop again, and hence transistor becomes off and capacitor starts charging. This charging and discharging of capacitor continues and rectangular oscillating output wave is generated. So by now you might have understood that none of the state is stable and automatically interchange its state from high to low and low to high. That's why it is called free running multivibrator. These are some calculations regarding astable multivibrator. Here, since we have seen that capacitor charges through R1 and R2, that's why the charging time TH is given by 0.693 into R1 plus R2 into C1. But since capacitor discharge only through R2, the discharging time is 0.693 into R2 into C1. So from that we get time period as TH plus TL, that is 0.693 into R1 plus 2R2 into C1. And from that we also can calculate duty cycle D, that is on time upon time period. So these are the equations. Now we'll see the simulation for astable multivibrator. Yeah. So this is the same circuit we have seen before, but now we'll see its functioning. Yeah. First we'll see astable multivibrator with R1 R2 of equal values, that is 1 mega ohm and 1 mega ohm. So when we run this circuit, here you can observe that on time is more than off time. So since we have seen formula for duty cycle is R1 plus R2 upon R1 plus 2R2 into 100. So if we want on time and off time nearly equal, then R1 should be eliminated from the equation. We can do this by taking R1 too much less than R2. So here I will make R1 say 100. Now if I run this circuit, we can find that on time and off time has nearly become equal. And you can also see that while charging, that means while on time, capacitor charges through R1 through R2 to the C1, but while discharging, capacitor discharges only through R2. It doesn't discharge from R1. From this simulation also you can verify the formulas for the on time and off time. Now, monostable multivibrator. This is a circuit for monostable multivibrator. It is a retriggerable mono-short pulse generator. The name monostable itself indicates that it has only one stable state. The unstable state in which it enters on triggering is called quasi-stable state. As shown in the circuit, there's an external resistor, capacitor and push button for trigger switch. The charging time constant of this RC network determines the duration of stable state, or we can say a pulse width. We can transfer the multivibrator from stable state to quasi-stable state by using push button as trigger. Now let's see its working. The output of the monostable multivibrator remains in its stable state until it gets a trigger. So when power is turned on, output is initially low. Initially, the internal transistor and external capacitor are shorted to ground because output is low. This state is considered as stable state. In stable state, output is at low voltage level. As we know, when voltage at second pin of IC555 goes below 1/3 VCC, output becomes high. This high state is quasi-stable state. This trigger causes the transition from stable to quasi-state. So when we press button, voltage at second pin becomes less than 1/3 VCC and output becomes high as RS flip-flop sets. Then Q bar becomes low and discharge transistor is cut off and capacitor starts discharging towards VCC through R1 with time constant R1C1. As capacitor voltage increases beyond 2/3 VCC, it resets the internal flip-flop, thereby turning off 555 timer. Thus, output goes back to its stable state from quasi-stable state. So you have seen in which way a monostable multivibrator is different than a stable multivibrator. In a stable multivibrator, it is free running. That means it automatically changes state from high to low and low to high. But in monostable multivibrator, if it is not triggered, it's remain in its stable state. But when we supply trigger through push button, it changes state and it remains in that state up to the time as long as its RC time constant. That can be calculated from R1C1. And after that determined time interval, it again comes back to its stable state. So now we'll see the simulation for the same. Yeah. So this is a circuit for monostable multivibrator. If you keenly observe, now this circuit is running. LED is in off state. That means by default it is in off state. So when I will press the push button and give the trigger, LED is on and in it remains for a specific time, and that time interval is given by 1.1 into R1 into C1. Since R1 is 1 mega ohm microfarad, so the calculation becomes 1.1. That means it remains in on state for 1.1 seconds. You can observe that. So that's all about IC555 and it's working as monostable and astable multivibrator. So for homework, you can search for bistable multivibrator and try to figure out how it is different from multivibrators we have seen right now. and also its applications. Thank you.